Okay, so this is lecture 15 of our oh, sorry. All right. Um, um, Welcome to the computational microelectronics lecture 15. So currently we are working on diffusion simulation. So you have already done the diffusion simulation of a simple case. So today we will talk about some additional stuffs including electric field effect. So I think that is the main topic of today's lecture. Before starting our that electric field related discussion, first of all let's get started with this boundary condition. I remember that actually one of our students came to me at the end of our previous lecture and asked me that question about boundary condition. So now let's think about our previous boundary condition. At the time, so we in this one-dimensional case we have two boundaries. So this is top and bottom, or sometimes we write down or draw left and right. And at the time, so the condition we have applied was just this one. There was no terms related with diffusion of our species. So it means that even though time elapsed t from 0 to certain t, there will be just no change in this dopant density. So please think about our previous example. So this is position x, and initially it was highly concentrated, and our observation point or our boundary was placed far away from this highly concentrated point. After that, time has elapsed. Then what will happen? So we will have a more broadened distribution. However, still it is true that our boundary points located here and there are far from this localized case. So by applying this seemingly inaccurate equation, so of course we introduce a little error in our C density at that boundary point. However, that does not affect anything in our numerical calculation result. That was our justification for certain boundary condition applied in the previous lecture. But let me just think about this case. Yeah, if we select this boundary far away from the peak point of our distribution, it's okay, but we have to consider more realistic case like this. Let's say that this is the silicon surface and here we have air or gas something, and in usual case we just introduce some implanted dopants into our silicon, and it is not placed in the center of our silicon wafer. So silicon, let's think about silicon wafer, and its thickness is around 600 micrometer. However, implanted dopants are just placed just nearby our top surface because we have introduced our atoms from the top surface. So if we have to simulate the diffusion of these atoms, then usually what we can do is take this point, the interface between air and silicon, as one boundary, and somewhere here we select another boundary. Actually, selection of this boundary doesn't make any difference whether we select this boundary to here or there or there or there, as much as our final distribution just looks like this. If our final distribution looks like this, then problem occurs when we select in this way. If we have this boundary point, then certainly that will introduce the distortion of our solution. So it is not desirable. However, if we select this way or that way or another way, that doesn't make any difference in our numerical solution. Okay, so usually, so this boundary point can be well established and it's okay. But point is here, this top surface. So we cannot extend the boundary not placed here but here, for example. Okay, let's say this is the boundary or this is the boundary for our diffusion simulation. But that doesn't make any sense because these points, the upper points, are corresponding to gas phase. So it is not the interest of our simulation. So anyhow, our boundary should be placed in that point. And as you can see, if this green line is corresponding to our final dopant distribution, then it certainly means that we have to anyhow consider the reasonably good boundary condition at this top boundary. Means that in this case there is no longer negligible dopant density. We have to consider the dopant density. Then how can we do that? That is the main one content in our lecture today. So today we will consider at top surface zero flux. Zero flux means that okay, here we have impurity atom and the atom is diffused to the top surface. After that, we assume that there is no such a case like escaping from this silicon and just jump into the air and become a gas phase and goes away from this silicon substrate. It is not allowed. So the flux from silicon to air is not allowed. That will be implemented in this case, and the result just looks like this. Here we have a new boundary condition related with this point. So however, when you have a look at this number, maybe you find that the diagonal component is just -2, but here we have 2, not 1. So why do we have this kind of boundary condition? Let's just simplify this point. Okay, so please go to this integrated form. So in many cases, our equations are written not in its original form, but once integrated over control volume. So this is our original equation to be solved, and instead of taking this value just like its own dimension, usually we integrate this value. So a certain range over a certain range we integrate it. Please note that in our uniformly spaced grid points, so please make a comparison for the control volume. So if I use a blue color to represent the control volume of each point, how does it look like? So in this case, maybe this blue range will be assigned to this second dot. And please think about this third one. Yes, you may feel that this is the right control area. Then obviously the next question is, how about the situation in the very first node? So can you write down? So for example, can you write down in this way? Certainly not. It is because our domain is not restricted to expand over this one. Our domain ends at this point. So simply speaking, if we just draw the control length or control area, control volume, whatever, in this case we have to have half of the other one. So that is a simple reason why we have a different coefficient for this one. So in our case, for example, let's think about x plus and x minus. So usually, for example, for this node, what is x plus and x minus? The upper and lower limit of our integration. For this node, this point would be x plus node, and this would be x minus node. Then please think about the x plus and x minus position for this node. In this case, of course, x plus will be placed here. However, your x minus in this time is placed here, not in this case. Well, then let's try to evaluate these two numbers. Then how does it look like? In this case, the flux defined at x minus point should vanish. Why? It is because this is the zero flux boundary condition we wanted to apply at the top surface. So it is understandable. And how about the flux at this x plus position? It's okay because we will have just d, and the distance is delta x, and c at x1 minus c at x0 will be a really good approximation to these values at the midpoint. It's because x plus point in this case is just placed in the middle between our x0 point and x1 point, so it is quite much reasonable to place in this way. Okay. Well, up to now we have done it, but it is a little bit difficult to understand why we have number 2, not number 1. But please think about this left hand side term also. So in this case, we have to make a time derivative of integrated dopant density. So simply speaking, we have to have a time derivative of a certain quantity, and this certain quantity means that the carrier density, dopant density integrated over our control volume. Then how can you express this integration using discretized quantities? So my suggestion is, of course, this one should take its node value x at c at x0, and we must multiply the difference between x plus position and x minus position. But please try to answer what is the value of this x1 minus x0. What is it? In usual case, that would be just delta x. So if we consider, for example, this point, then their difference is defined as delta x, and their difference is written as delta x. However, we are now talking about the boundary point places the leftmost position, and in this case the difference between two boundaries of our integration would be just half of it. So that will give us this number. So that's the reason. So please remember that all of our equations are normalized, and when we normalize this equation, we are based upon the value of delta x equal to 1. So in this case, these delta x values can be just regarded as a normalized quantity 1, and this one is just can be regarded as a normalized value 1. So the origin of our strange coefficient number 2 comes from this one. This 2 is just go to the right hand side, of course manipulated a little bit more. However, we will have this form. So it means that in this implementation, let's say that happen to be, oh, you feel okay, not this way, but I love to write down in this way because it looks more reasonable. Let's assume. Then what will happen? You are now introducing a long boundary condition in your system. Then you will have strange behavior. You may see strange behavior of your equation. So this is quite much important. So simply speaking, even when you impose the boundary condition, you should be consistent with other treatment for other nodes. So in our case, we have uniform treatment for our equations. Simply speaking, we just want to integrate our equations over certain range, and that is normalized. So please don't be confused with other boundary conditions. Okay, so do you have any question about this boundary condition? No? Maybe the one possible question is, okay, up to now we have introduced just zero flux boundary condition. Then how about other cases? For example, some impurity atoms can escape from this silicon substrate and just enter into air or gas and becoming certain different species and yes, removed from our scene. Yes, it is possible. So in that case, maybe we can introduce a certain non-zero number or non-zero function in this flux term. So your boundary condition is closely related with this term. So that is really depends on your boundary condition. When you have a new situation about your dopant segregation, then please revise this part. Then of course that will introduce a certain change in your matrix form too. So you can understand this one. Okay, so now let's think about the same problem. Previously we had thought about the diffusion in this Gaussian shape, and after time has elapsed, then we have a more widened behavior of our dopant profile. It was possible because previously we had the boundary located here and there. However, although looks quite similar, but right now we are saying that this is the boundary of our simulation domain. So if you just apply the previous boundary condition, then the value at this point can never change. So that is not possible. In this case, with the proper boundary condition of zero flux, actually now you can see that here is time elapse. Now you can see the decrease of this peak value, and you can see that since we are now talking about the zero flux, so you can see that also gradient of your C density, impurity density tends to be 0, because if we allow such kind of a high steep change here, then it is related with high incoming flow or outgoing flux from this node to into the substrate, but it is not possible. So yes, so please understand the situation. Okay, so simply speaking, a boundary condition is critically important, and however, boundary condition is not coming from the bulk diffusion equation. We need additional information sent from other consideration, the consideration about physical reality in our simulated system. So that is a kind of different domain, and when a boundary condition is given, then we are now able to implement it properly. Okay, so now let's think about next topic. Next topic is related with multiple dopants. This is particularly important for realistic case. For example, if you are working with just laboratory experiments, then you can just prepare quite clean vapor and just introduce your atoms, impurity atoms, by performing an ion implementation. After that, you heat the vapor up, then cut the vapor and takes the seams profile, then yes, you will have a certain beautiful grapes. However, in reality, your ion implementation is not done just a bare vapor. It's not. It always has previously doped dopant profile, and more worst cases, usually you switch your polarity. For example, what you wanted to do usually is make a p-n junction. How can you make a p-n junction? First, fabricate a p-well, relatively low doping of your p-type dopants. After that, you introduce n plus implementation on the p-well. Then you will have n plus p junction. Quite similarly, you may have n well, a region with relatively lowly doped n-type dopants. After that, you implant your p plus doping onto it, so you will have different polarities. So the situation is your ion implementation just not looks like this, but there is already existing dopant profile. For example, let's say that this is your donor profile. Then at the same time, this does not exist alone, but there is also another acceptor profile. So in this case, well, I increase the temperature up to, for example, 1000 Celsius, but only donors diffuse and acceptors do not move. That's not the case. If you apply certain heat to your vapor, then both of or all of your dopants are moving. Even your host material, silicon, they are moving. Of course, since they are identical, although they are exchanging their positions, we cannot see actually their movement. However, it is true that every atoms in our silicon vapor are moving under the elevated temperature. So we must consider multiple dopants, not only phosphorus, not only boron, but their simultaneous movements are required to be simulated. So that's the point. For example, let's say that here we have boron. Oh, I think that screen is stuck. Let's wait for a while. Okay. So now here we have let's assume that two species, boron and arsenic, and we may have two different approaches. Okay, during the time evolution, borons are diffused and arsenics are diffused. They can be treated individually. In my opinion, as much as they do not interact to each other, it's okay because they are independent. However, in many cases, they are affecting to each other, so we must consider a coupled system of these two species. In this case, in the second approach means that we are solving the diffusion of these two species simultaneously. In this case, our solution vector becomes twice larger. So previously our solution vector just contained C, yes, so C means that dopant density, but now let's say that we have a boron and arsenic, then we have to apply, for example, boron density at a certain position and at the same time arsenic density at the same position. We must have two different species and number of unknown variables should be doubled. That is quite obvious, so maybe it is not that difficult for you to understand this doubling. If we have more and more species, what will happen? Yes, you must increase the size of your solution better, further and further. Yes, it's not that difficult to understand. Okay. So now we have a quite a simple example. In this case, there is nothing, no interaction between them. So let me just consider this example. Here we have boron and here we have arsenic, and please have a look at its diffusivity. So diffusivity of boron in this particular example is 1.4 times 10 to the minus 14 square centimeter per second. Don't be amazed or surprised by this order. So why you must be surprised is actually when you have your conventional d values for your electrons and holes, then please think about the order of your dn or dp. What is your expectation? The value would be just about 1 square centimeter per second, and of course depending on situation this dn value can be a little bit higher or a little bit lower, but point is their orders of magnitude is just around this 1 times or 10 or 0.1, something like that. That is the orders of diffusivity of our electrons, charge carriers, holes, charge carriers. But when you have a look at this number, this is really amazingly small number. This is 10 to the minus 14, 10 to the minus 15 square centimeter per second at the same one. And you know that this is not for 300 Kelvin. I'm not talking about room temperature. Room temperature, we have even much lower diffusivity. This is a really meaningless number. This number is taken from, for example, about 1000 Celsius. So means that this is the real situation. We heat the vapor. So even in this case, D value is extremely small compared with our electrons and holes. That's the reason why our electronic devices are working so fast. However, in our diffusion simulation, we must wait for 1 minute or several minutes or several hours are required to have meaningful difference in the dopant distribution. So please don't be confused with this huge difference in the same quantity diffusivity, because electrons and holes, they are almost free carriers, and in this case boron and arsenic, they are atoms much heavier than electrons and holes, and they are tightly bound to the silicon substrate, silicon crystal. So it is not easy to them to diffuse over the silicon crystal. So anyway, now let's think about this situation. Originally we have uniform boron distribution. So boron is a p-type dopant, and this is density is 10 to the 17. Yes, this is quite reasonable, and this is just corresponding to our typical p-well density. So of course, I'm not saying that this uniformity is extended over entire our vapor. Our vapor thickness, if we just draw in this scale, starting from here 0 to here 300 nanometer, it means that the actual size of our vapor is just 2000 times longer than this scale. So this is just 300 nanometer, but vapor thickness is typically 2000 times thicker. So we are now just observing just interface of our entire vapor to support our electronic devices, and in this quite a short range, we can treat boron density as just constant. Of course, what will happen in reality? So boron density extends over quite a long time, around a few micrometer scale. For first a few micrometer, so still we can treat this boron density as a constant, and eventually it will roll up and go to the zero. However, since our simulation domain is just restricted to the first 300 nanometer, so it is completely okay to say in this way. Okay? And usually this boron is predefined by fabrication of a p-well. After that, you just perform the ion implementation of your arsenic atoms. So in order to fabricate your p-n junction, so what will happen? So now we have peak point just 20 nanometer down from our interfaces. We wanted to make quite a shallow junction between this N plus and P. Yes, at this point, maybe this is the metallurgical junction between these two dopants type. However, when you just make an ion implantation, these arsenics are not activated at all, so you must apply certain heat to activate it. So let's do it. So after 10 minutes at about 1000 Celsius, then this is the result you may have with given diffusivity and given initial dopant profile. Okay, now you can see that if we apply certain heat, and yes, peak point doesn't change much. Yes, because always it just diffuse over non-peak points. So usually peak does not move quite fast, and after that, here you can see that the extension of a metallurgical junction. It is because previously highly concentrated donors are now diffused and their concentration is a little bit blurred. So now we have a widened junction. From the viewpoint of fabrication, usually this I can say excessive diffusion of our high density dopant is regarded as a bad thing, because usually we wanted to make a quite shallow junction. So that's the reason why we introduce a low energy ion implantation to our dopants. So we wanted to make quite a shallow junction. However, in order to activate these dopants, we must apply certain heat, and it introduces a certain redistribution of our dopants inside the semiconductor substrate. So anyway, that is the situation we can expect from our diffusion simulation. Oh, then maybe you feel a little bit strange. In the case of boron, there is no change at all. It is just still 10 to the 17 per cubic centimeter. Why do we have just no change in our boron concentration? It is obvious because boron initially was uniformly distributed, and this is the final solution of a diffusion simulation. So already it is reached at uniform distribution, although we solve diffusion problem, but that does not make any difference in our boron concentration. So it's not that interesting. So it means that even though we have already included boron in our simulation, but boron doesn't play any role in this case. It's not that interesting. However, now think about the case shown here. Well, although you may say that it's not that interesting, so if you have a look at this dopant profile, then you immediately understand this is nothing but M plus P junction. So since this is the M plus P junction, here we have M plus dopant, and here we have a P-type resin. So if we introduce an additional holes into this system, yes, for example, let's say that if we introduce a certain hole here, then what will happen? You have a PN junction, and at the metallurgical junction, you just inject a hole into it. Then it will feel strong repulsive force from your M plus region, and it will be pushed back to your original p-type region. So the force exerted on this additional hole is originated from the electric field. It means that here we have a strong electric field in this case. So that is the key. Since our borons and arsenics are distributed locally at a certain point and that certain point, even in this case we have internal electric field, and this internal electric field can make certain change in our diffusion simulation. That is the point. Okay, so now let's just think about this one. Up to now we have considered only the diffusion term. So previously the flux was written as this diffusion only. Gradient of concentration is involved, and here we have a minus sign because our flux is always from high density region to the low density region. However, if we have certain velocity set by other reason than the diffusion, then actually we must add these additional terms. Think about this one. Here we have a box, and here we have a small jar. There is a jar, and this is a perfume jar. So now we just open the jar. After that, what you can expect is from this jar there will be diffusion of perfume molecules, and you can smell it. It's okay. But instead of that, now let's say that this box, the system itself is constantly moving toward this positive x direction with a certain velocity. Then if we are observing this point, and let's say that this is the origin of our observation. If this velocity is 0, then what we can say is, okay, initially all of perfume molecules was concentrated at the position of jar, and after the seal is removed, then now it diffused, and it diffused. After a long time later, the entire container in this blue box is covered by the uniform density of a perfume molecule. That is the situation we can expect. However, if this container itself is moving, then what will happen? In this case, there will be the position of this perfume molecule is in center point is no longer centered at this point. There will be certain change of their center point. Their average motion should be added. Quite similarly, so this first term, diffusion term, just to describe diffusion of our atoms. However, let's say that all of them are just pushed from one point to the other points, then their collective motion should be added to this case. Then how can we consider this velocity? Of course, there can be many different mechanisms. However, what we want to do is just to drift term, the electric field effect. So if we have an electric field effect, then that will introduce this kind of average velocity. So if we have a negative charge, and that will introduce a certain velocity, and of course if there is a positive charge, then we will have this one. Since we are now talking about our ionized dopants, so in this case, if we are considering donors, then they should be regarded as positive charges. And if we are considering acceptors, then they should be regarded as negative charged particle. So it means that once donors or acceptors take the place for silicon crystal, so they, in that case, they are called substitutional, and when they place takes that place, then they are ionized and they have a charge, so their movement should be described with this additional term considering the electric field effect. So now you have the picture. So in this case, if we have a PN junction, although it is not cooled down to the room temperature, even at elevated temperature, we have a PN junction. And PN junction, we always have the developed internal electric field. This intrinsic electric field or built-in electric field additionally push our dopants. For example, let's say that here we have n-type donors and they are positively charged, and here we have borons, p-type dopants, they are negatively charged. And please have a look at the sign or direction of electric field, built-in electric field. So what we can expect is, from the action of this built-in electric field, maybe our positively charged, our donors will be drained further into this deep substrate. Also, in the case of our boron, since they are negatively charged, they will further push it to this way. If we have only diffusion mechanism inside this system, then boron will be still uniformly distributed. However, if we include this electric field effect, then since we have additional driving force, so boron concentration can be changed a little bit. So please have a look at, let me just show you the, okay, so unfortunately I didn't show our previous result, so please visit our 2023 lecture material of lecture 9 at the time. So you can see the profile obtained from considering the electric field effect. It is no longer uniformly distributed, even in the case of our boron dopants. Okay, so let me just show you how can you include that effect in your simulation. Okay, so the point is, now we have to include this velocity. Then in order to calculate this velocity, of course, we must calculate electric field. And as you know, electric field under the electrostatic approximation, it can be obtained from the gradient of electrostatic potential with negative sign. So simply speaking, once we can generate or calculate electrostatic potential, then this problem is now over. Then how can we calculate the electrostatic potential? So let me just go to the more rigorous one. The rigorous one is, of course, just to solve the Poisson equation. Poisson equation is the equation for getting the electrostatic potential. So please try to solve nonlinear Poisson equation. Why do we have a nonlinear Poisson equation? In this case, we express our electron density and hole density as a function of our electrostatic potential. So electron density and hole density can be eliminated from the set of unknown variables, and just to solve one equation for electrostatic potential. Then in order to solve this problem, we need a little bit more information. What is VT? This is summer voltage, and summer voltage, usually when we consider 300 Kelvin, we just say that this is corresponding to 80.85 millivolt. But this is at 300 Kelvin. So since we are now talking about 1000 Celsius, of course you must change it to the reasonable value corresponding to 1000 Celsius. Okay, good. However, still you need additional number, intrinsic carrier density. And you know that intrinsic carrier density is also quite steeply changing when you change the temperature. When you have a higher temperature, then you have higher intrinsic carrier density. So therefore, when you solve your nonlinear Poisson equation, please do not use the value at 300 Kelvin. You must introduce the values suitable for 1000 Celsius we are currently assuming. So with this modification, now you can solve the nonlinear Poisson equation. Of course, you have to consider what is the appropriate boundary condition for this top surface and bottom surface. And yes, so please try to evaluate your electrostatic potential by solving nonlinear Poisson equation. Point is, this calculation should be done at each time instance. It means that, for example, you are now going from 0 to 600 seconds, and your, for example, time distance is, for example, let's say the 1 second. It means that you must solve your nonlinear Poisson equation about 600 times. Well, it sounds too cumbersome, but in order to do it correctly, actually this is what you have to do. So please solve nonlinear Poisson equation at each time instance with given dopant density. You know arsenic dopant density and you know boron dopant density, so you can solve it. Then by solving this nonlinear Poisson equation, then you will have this information, and from this one now you can generate the electric field, and from this electric field you can generate the drift velocity. And please add this term into your diffusion equation and solve that problem. Then that is corresponding to one step in your time transient. After that, if you take this diffusion simulation, then you will have a little bit different arsenic distribution and boron distribution. Yes. So since now we have slightly modified dopant distribution, your potential will be changed a little bit. Yes, please recalculate it. So in order to recalculate it, of course you must solve nonlinear Poisson equation. Then repeat this job again and again till you eventually arrive at your final destination 600 seconds in our example. So this is related with many times calculation of nonlinear Poisson equation. So this is computationally very heavy, but by performing this job, then you can always get the solution. Then maybe you can ask me this question: oh, how can we solve just nonlinear Poisson equation? Nonlinear Poisson equation always related to the equilibrium state, and we are currently considering the system under change. I'm gonna say our dopants are distributed and diffused all over the system, but how can we assume the equilibrium state? Please, in my opinion, this is a very important one. Here we have a system of arsenic and boron. We are interested with this one. And also we have a system with the electron density and hole density. Please think about the time scale, relevant time scales of these two systems. You know, in this case, the time scale is a few seconds or minutes or hours. And in the case of our electron and hole system, what is relevant time scale to respond to certain change? This will be just picosecond or nanosecond range. So although our arsenic and borons are slowly moving inside our silicon crystal, when its shape or its dopant densities profiles are changed, then our electrons and holes can almost immediately adjust their distribution according to this slow change of dopant distribution. So this is, simply speaking, they are quite quick and they are quite slow. So since this quick system is attached to the slow system, this quick system can be regarded as at equilibrium almost always. So that's the reason why our nonlinear Poisson equation, the system equation for electron and holes, can be regarded at its equilibrium state. So we can solve the nonlinear Poisson equation, and instead, in the long term, in its slow evolution, we can solve the diffusion equation. Okay, so this is the, in my opinion, more rigorous approach. However, in reality, when you have a look at the available codes for dopant distribution, so usually they don't want to apply this rigorous approach. The reason is quite obvious. What is the reason? In order to make this implementation, you must solve nonlinear Poisson equation always. So this is really heavy computational burden. So when you have a look at certain technical documents or previous literatures in this diffusion simulation, so instead of that, they wanted to introduce certain approximation. Simply speaking, so everything is quite acceptable. However, the critical step for simplification is charge neutrality. Charge neutrality here means that at every point inside this system, net charge density becomes 0. So of course, this does not hold for p-n junction. When you have a p-n junction, usually you have a depletion of your charge carriers, electrons and holes, and you really have space charge losing. However, in this simulation, in this approach, approximate approach, they means that the developers of this dopant diffusion simulator assume charge neutrality. Then in this case, electron density and of course hole density can be expressed as just a local function of donor density and acceptor density. So when you have donor density and acceptor density, then you can immediately recalculate electrostatic potential. When you know electron density, then you immediately know electrostatic potential under the condition of equilibrium. When you have an equilibrium case, then you have a one-to-one correspondence between your electron density and electrostatic potential. Okay, so you must understand this is really a crude approximation. Well, charge neutrality does not hold in this p-n junction, but anyhow, when they apply this one, it is much better than nothing. So if you don't consider any kind of electric field dependency, then you will have just quite boring distribution function here. However, if you include your electric field even with crude approximation of charge neutrality, but you can partially include that effect into your system. So please note that nowadays we are living in the era of quite a fast computer available to us. Even to us means that the researchers in academia. However, when our former researchers start the simulation of this physical quantities diffusion simulation, at that time computing resources were quite expensive. So they wanted to reduce the computational burden as much as possible if that is allowed it. So they have invented such kind of approximation. So now you have a homework announcement. So simply speaking, please revisit our previous example, the example of arsenic and borons in a same position or same system. The last example means that our previous example. And now please consider the electric field effect. Now we have studied two different approaches. One, using rigorously solving the nonlinear Poisson equation, and another one is just to approximate the electrostatic potential under the charge neutrality condition. Please try both of them and draw the dopant profile after 10 minutes. So please try the option of nonlinear Poisson equation. Of course, in order to calculate this one, you need thermal voltage and intrinsic carrier density. So I will give the numbers. So intrinsic carrier density is 7 times 10 to the 7.12 times 10 to the 18, much higher than our previous value 10 to the 10 at room temperature. So please use this high density. So simply speaking, so this is corresponding 7 times 18. So simply speaking, 7 times 18 means that where can you find it? 1, 2, 3, 4, 5, 6, 7. So this is now our intrinsic carrier density. So simply speaking, here although we have a boron density here, that doesn't introduce much in our system. So now only it is corresponding to the N plus ductal region and intrinsic region, and here we will have a certain electric field between them. So you will have certain change in your final distribution. And please note that for your reference, please visit our last year lecture and lecture 9. There you may find the result out of not solving fully this nonlinear Poisson equation, but using charge neutrality approximation. Please be inspired by that solution and do more rigorous job with nonlinear Poisson equation. Okay, do you have any question on the lecture contents or homework problem? So, if not, so I want to wrap up today's lecture, and please prepare this homework. I think that this homework is more involved than our previous one, so you have 5 days to solve this homework problem. Okay, then see you next Tuesday.